using controllability and observability criteria. So we consider the system given by the state equation here, and in this state equation I have two parameters a and b. So I have two inputs u1, u2, two outputs y1, y2, and the state is of dimension 3. We have to find the values for A such that the system is controllable, so we can understand that A is a link between the input and the state, so it is related to the controllability of the system, whereas B is in the observation matrix and is related to the observability. So here I have my system, and for the question number 1 I will see what happened for the controllability of the system. So the controllability, to check the controllability, I have to check for the controllability matrix, which is given by the matrix B, and I have to concatenate with the matrix A times B, where A is this matrix and B this matrix. So of course it will depend on A, and also A square B, and I stop here because here I have n minus 1, where n equal to 3, the dimension of the state. I have the following Python program which use SymPy. So SymPy is for symbolic computation. I have to introduce the two symbols A and B, the parameters. I define the matrices A, B, and C, which correspond to these matrices defined here. C is here, and we can see that the symbol A is in the matrix B, as it is the case here. Now I will print, so pprint means pretty print, so that you have a better visualization of the matrices A, B, and C. And I will form the commandability matrix JCOM here, where I will join the rows of the matrix A, AB, and then A square B. And after I will print it on the screen. I run this program, and I can see my matrices A, B, C, and the controllability matrix, which is given here, which depends on A. So I take this matrix, I take the commandability matrix, and I will compute the rank. So here I will write this one V1, V2, V3, V4, V6, V5, and V6. And to show that it is full rank, I will try to generate the vector from the canonic basis, so E1, E2, and E3. Okay, so I can see that E1 is equal to, for instance, V3 minus V1, so I can generate E1. Now I can generate from V3, I can generate E3. So E3 is equal to 1 divided by A multiplied by V6. Okay, and now using V1 and V6, I can generate E2. So E2 is equal to V1 minus minus E3, so 1 divided by A, V6. So from the V, I am able to generate the vectors from the canonic basis. As a consequence, it is full rank. Full rank, except if A equal to 1, If a equal to 1, then the rank is 2 and not 3. As a consequence, to answer the question for which a my system is controllable, it is for a different of 0. So I answered the first question. Now, for which values of b the system is observable. So for this, question number 2, I will generate the observability matrix, which is equal to C, CA, CA square. I take the following Python program, which also uses SIMP. Here I don't need this anymore because I am interested by the observability matrix. But I will join through the colon and not through the line. This is why I have a colon join of C, CA and CA square, and it forms the matrix gamma ops. Then I will print it, and to make things simple, I will not compute the rank by hand, but directly ask to Python to give me the rank. Also for the commandability matrix and also for the observability matrix. I go here, I run my program, I can see the observability matrix, and I can check that the rank is 3, so for generic A, not for A equals 0, and the rank for the observability matrix is 2. So I can easily check that I cannot generate all vectors from this, and we can see, for instance, that the first vector and the last vector, column vector, are both proportional. It means that the rank of gamma ops is of 2. The system for all b is not observable. Now I switch to the last question, and I have to draw the block diagram of the system. First, put my 3 integrators corresponding to the state of the system: x1, x2, x3. The input of each integrator is x.1, x.2, x.3. So I consider the first for x.1, and I have here that it corresponds to the sum between different quantity x1, x2, now for x.2 I will have x2 and u1. I will put u1 later. And for the last one, x.3, I will have here x.3. Now for u1, u2, here u1, u2. So u1 is involved here in the first column with respect to x2 and x3. And now for and x3. And now for u2, it will be involved only for x3. So here I have an integrator in A, and I go to this sum. Now for the output, I have 2 outputs, which corresponds to y1, y2. And for y1, I have the sum where are involved here x1, here x2, here b, and due to this, for y2 is involved only this one. Okay. The controllability and the observability cannot be directly obtained from the block diagram. I can see different things. For instance, I can see that when b equal to 0, then x3 will not affect the output. So we can understand that if b equal to 0, x3 is not observable. But assume that a equal to 0, for instance. So this does not exist anymore. I can see that u1 will affect x2, will affect x1, and will also affect x3. So indeed, u1 will affect x1 through x2. But it's not. It does not mean that x1 is not controllable. Why it is not controllable, the system? It is because when I want to increase x2 via u1, then I am obliged to increase also x3 in the same manner. It means that the difference between x2 and x3 is not controllable.